Okay, so the first thing is remember there's no school Thursday or Friday, so don't come. It's MEA. I don't know what MEA is for anymore. We used to have to go to meetings and stuff, but now they don't make us go to meetings, so it's just the vacation we all crave now. So no school. Thursday or Friday. And the building is probably closed is my guess, although I'm not sure that's true. So if you're going to come here, at least check the schedule first. And second, does anybody have any homework problems you'd like to see me do? Anything? Yeah.
I have a question for A and B.
Okay.
About the T arrow that was in the answer key. I didn't understand why that was.
Okay, let me pull that up. So this is in free body diagrams, number 4. This one? Okay, yes. So I think probably the confusion is just kind of with the way that it's drawn. In order for this to work, I mean, there are 2 ways this could work. One is that those are just initially leaning against each other. And if you applied that 500 Newton force to the 20 kilogram cart, they would just separate from each other. So that's a possibility. The other way, I guess the way that I probably did it was assuming that those are attached in some way. And you can think of it as like them being attached by a tiny little cable that's pulling the back one from the front one. It sounds like that's what I did. So let me just draw through the thinking of that. This is actually what I'm talking about today, but I'll do this and then I'll backtrack and. Okay, so where'd that go? Okay, so it's 20 and 10, 500 and 200. Okay, so free body diagrams, number 4. What did I say the masses were? I have a bad memory. Uh, 20 and 10. Okay, so this is 10 kilograms. This is 20 kilograms. Nope, I drew them backwards. So this one's 20. This one's 10. And you have a 500 Newton force and a 200 Newton force. Okay, and in the drawing, that cable between them isn't shown, but I think if I were to make this problem today, like I would just put that cable in there so it's clear. Okay, and let's just go through the free body diagrams. And I think when you're doing free body diagrams, what you really want to do is just think about the rules in each step, you know. So I'm going to try to just carefully talk through like the rules of these. So first I'll do the one for the 20 kilogram. So first draw an outline without any internal details or external objects. So there's the outline of the 20 kilogram cart. And then draw the weight force. So that's a downward force of the mass times 9.81. So 20 times 9.81 is 196.2. And now that you have the weight force, just go around the boundary looking for any places where the outside world makes contact with the boundary. There's this force here of 500. Then at the wheel, so I'm just sort of going counterclockwise around from that 500 Newton force. So the next one you get to is the wheel. That's a pushing contact. So that force is going to be perpendicular to the surface of contact, which is the incline, and toward the chosen body, so into the wheels. You know, if you think of the surface of contact as this incline, the force is perpendicular to that. There's really one force on each one of those wheels, or really there's 4 wheels and there's one force on all of the 4. But we're treating these as particles, which means all the forces act in the same place anyways, because we're treating this thing like it has no dimensions, no lengths. So this is the direction of that pushing contact. You can give that variable whatever name you want. I'm going to call it N for the normal force. That's a variable name that people use often for pushing forces from the ground. And now if you keep going around, you get to the cable that's connecting this to the other body. The cable force, the rules are parallel to the cable and away from the chosen body. So parallel to the cable means like this. Away from the chosen body means it's this direction out of the 2 that could be parallel. And I'll give that the name T. Okay, so we got those 4 forces. Let's look at the picture again. Is it surprising that I'm not putting the 200 Newton force in there? That 200 Newton force is just, it's part of the problem. It affects the problem, but it doesn't act on the boundary of the 20 kilogram cart, and so we just don't include it, you know? It's just that simple. You don't have to think about whether it affects the problem or not. You just have to think, does it act on the boundary of the thing that I'm isolating? And if it doesn't go in there. Okay? And now the free body diagram of the 10 kilogram cart. So there's the outline. I guess I'll start with the front again. So on the front of this, no, I'm going to start with the weight again. I might as well always start with the weight. So the weight force is 10 kilograms times 9.81, so 98.1 newtons. And now I'll go to the front. There's a force applied by the cable. Well, cable forces are parallel to the cable, away from the chosen body. And since this is the same cable as this one, we'll give it the same variable name. I'll talk about that a little more in class today. Now, if I keep going around, I get to the wheels. That's a pushing contact. And the rules for a pushing contact are perpendicular to the surface, so perpendicular to this. Toward the chosen body, so from the ground toward the wheels. This is a different force than that one, so I think I'm going to call this one N1 and call this one N2. Okay, those are different variables. And then keep going around, nothing, 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 until you get to the top. And then that force of 200 newtons is applied like that. The 500 doesn't show up on this one because it acts on the boundary of the other one, not on the boundary of this one. Any questions about that? And notice that now we have all this. If we know the angle of that incline, we could figure out, in the vectors problems, you figured out what these vectors were as components for stuff like this all the time, right? So you could come up with the components for all these, add up those forces, put them into Newton's second law and calculate the acceleration of this, the forces between the bodies, stuff like that. And that's the next thing we're heading towards. Okay. Any questions about this one? Yeah.
Yeah, so I know you have a cable on it now.
Yeah.
But so that 200 Newton force.
Yeah, don't you wish you could do what I do, just change the problem to fit whatever you're...
Yeah, that would be great. What's like a force like that 200 with wheels, would it still increase friction force?
There's no friction in this. Whenever I drop wheels, it's sort of implying that there's no friction. If that was friction, if that box was just rubbing along the incline, yes, it would increase the friction. And it also, even without friction, it would increase the value of that force N2.
Okay.
Yep. And all that stuff would just be calculated from plugging these into Newton's second law. Any other questions? Okay. Any other homework problems you'd like to see me do? I know sometimes it helps to just see someone talk through it instead of just seeing the solution posted. Okay, well, I'm planning to just talk about some of this stuff today. That fits right into what I'm planning to do today. So first, I want to just talk generally about the rules for free body diagrams. I know you've already seen a lecture on that, so I'm not going to go into a lot of details. But I just want to sort of go back over the rules for drawing free body diagrams and how the different force types show up. So when you're making the free body diagram, the first thing is you have to draw your chosen body. And so to do that, you draw an outline, only an outline, with no internal details. It's not an art class or anything, You're just drawing an outline to make it clear to me and clear to yourself what the boundary is between what is in your in crowd and what's out in the outskirts, You're just trying to make a distinction between what's in the chosen body and what's out of the chosen body. So no internal details. No outside objects, because the whole idea of like what the free means in free body diagram is that you're totally separating your chosen body from everything else, and everything else is just from that point on going to be represented only by forces. Okay, so if you draw the ground in there, or you draw something else that's not included in your free body diagram, you're just creating confusion about what's in and what's out, Then draw the weight force. So that's a downward vector with a magnitude of mg, the mass, times 9.81. And then the last thing is a fourth vector representing each contact at the boundary. So you're just going mentally around the boundary of your chosen object, looking for the places where the outside world touches it. Sometimes those can be forces that are like applied to it that are given, like the 500 and the 200. And other times it's just like, okay, there's an object touching it, so I have to figure out what that force is. Here's an object touching it, I have to figure out what that force is. Once you've dealt with all the things contacting the boundary, you know you're done. Okay, so this is the trickiest one of these four to do, how to represent those contact forces. So I just want to give a little summary of the different contact force types. The first one is pushing contacts. And the rules for a pushing contact are that this force is perpendicular to the surface of contact and toward the chosen body. So for example, well, this is almost exactly the same as the example that, the problem that I just did. But say you have this thing, this little cart thing that has a mass of 5 kilograms, and let's draw the free body diagram for that. So first, draw the outline with no internal details and no external objects. Draw the weight force. 5 times 9.81 is 49.05. And now the surface of contact is this incline. So the pushing force is perpendicular to that surface toward the chosen body, and that's it. How do you know that a force is a pushing versus a pulling contact? A pushing contact is preventing the two things from merging, and a pulling contact is preventing one of the things from escaping the other thing. Okay, so you can think of it that way. Like in this case, what if that ground wasn't providing any force at all? What if that ground turned to air all of a sudden? The 5 kilogram cart would go through the boundary into the surface. You see that? And so that has to be a pushing contact. Okay. A pulling contact is like, if the two things are connected to a cable, that cable is preventing those two things from separating. Okay. So you can always think about it that way. Is it preventing the two things from merging, or is it preventing the two things from separating? So now that I've done the weight force and I've done a force representing every place the outside world is in contact with the boundary, I know I'm done. There's no like confusion about like, oh, did I forget anything? You're done once you've done that. So that's sort of a nice thing to kind of center yourself with, Any questions about that? Okay. So the most important equation in this class is Newton's second law. We'll talk about that some today, but there's another important, it can be written as an equation, it can be thought of as just sort of a concept, but that's Newton's third law. And I'm going to bring up one application of Newton's third law right now. You don't have to write this down, but Newton's third law is the thing, you've probably heard the phrase like, for every action, there's an equal and opposite reaction. That's a pretty hard to get anything mathematical out of that sentence. But what it means is that the force vector, one object applies to this, object A applies to B, is equal and opposite to the force vector object B applies to A. Okay. And I'm going to give you sort of separate ways to think about that for each of these contact force types. So Newton's third law says that the pushing force let's say object 1 applies to object 2 has the same magnitude in other words, we're going to use the same variable name as the pushing force object 2 applies to object 1. Okay, so let me show you an example of this. So let's say that we have a 2 kilogram object sitting on top of a 3 kilogram object. So I'm starting out with a free body diagram of the top thing, okay? There's the weight force, and then there's the pushing force. So I'll call that N. And then go around the boundary, there's no other contact, so that's it, okay? So now I'm gonna draw the free body diagram of the 3 kilogram cart, and this is where you're gonna see that Newton's third law thing, okay, how that works. So free body diagram of the 3 kilogram object. There's the outline. There's the weight force. So that's 3 times 9.81, so 29.43 newtons. And now going around the boundary, there is okay. Okay, so there's a downward force, 29.43. There's a pushing force from the ground onto the wheel of the 3 kilogram. That's not, that's not related to the pushing force on 2 by 3. Okay, that's not applied. This force isn't applied by 2. It's applied by the ground, so that's going to be perpendicular to the surface of contact toward the chosen body, and I have to give that its own name. You know, it doesn't matter what you call it. I'm going to call it N2. There's nothing really special about that name N. It's just something that people use often for these pushing forces from the ground. But now keep going around and you get to that pushing contact. You get to the contact from the 2 kilogram cart, okay? Well, 2 and 3 are pushing on each other. They're preventing each other from merging. They're preventing each other from passing through that boundary. And so since we've already dealt with the force on the 2 by the 3 and given it the name N, I'm going to give this one the name N2, N also, okay? So this force is perpendicular to the surface of contact toward the chosen body, which this time means it's down, and the variable name is N. Okay, so what that means is if we calculate the value of N is 40, there's a 40 Newton force pushing up here and a 40 Newton force pushing down here, okay? Anybody have any questions about that? So the key thing, oh my God. It's one of those days. So the key thing that you want to think about is, you know, this N, that first one we defined, was applied on the 2 by the 3. So you have to give the same variable name to any force on the 3 by the 2. If you switch which one is applying the force to the other one, then you're using that same variable. Okay. Okay, so that was the pushing contact. So now we're going to the second type, which is a pulling contact. And I recommend just always thinking of pulling contacts as being those contacts being like via cables. So if something's pulling on something else, just imagine there's a little cable involved. That helps you figure out the direction of the force. So the rule for pulling forces is that this force is parallel to the cable not toward, away from the chosen body. So for example, if you have an object hanging from a cable, let's say that this has a mass of 2 kilograms. The free body diagram of this mass has the weight. That's 2 times 9.81, so 19.62 newtons. And then the force applied to it by the cable is parallel to the cable, away from the chosen body, and I'll call that T for tension. the magnitude of the force applied by a cable is called the tension. One thing to notice about cables, and this is, you can think of it as related to Newton's third law, or you can think of it as just a thing cables do. But if a cable touches nothing but pulleys, between bodies, okay, so if a cable touches nothing but pulleys between bodies, the direction of the force vector can change. You know, the direction of that pulling force can change, but the tension never changes. And that means that you can use the same variable anytime you're dealing with the same cable. You know, so the force that applies to one object is going to be the same as the variable you use for the force on one object will be the same variable you use for the other object. Okay, so let me show you how that works. So let's say you have an incline and a pulley at the corner. And on the incline, you have a cart, let's say that has a mass of 2 kilograms. And it's connected to a cable, and the other end of the cable is connected to a mass of 1 kilogram. And we want to draw free body diagrams of these two. Okay, so first I'll do the 2 kilogram object. So there's the outline. On your things with carts like this, there'll be a few problems like that. If you don't want to include the wheels, just draw the box. That's fine with me. Okay, so there's a weight force. That's 2 times 9.81, so 19.62. Then there's a pushing contact from the incline. It's going to be perpendicular to the surface toward the chosen body, and I'll call that N. And then there's a pulling force from the cable. It's parallel to the cable, away from the chosen body, so this way, and I'll call that T. Any questions about that one? So now, the reason I'm doing this example is so you can see when this other body is connected to the same cable, how I'm going to treat that, okay? So free body diagram of body 1, the 1 kilogram object. There's a weight of 1 times 9.81, so just 9.81 newtons. And now there's a cable force, like all cable forces, that's parallel to the cable, away from the chosen body. But the thing that's special here is that since this cable between these two bodies only touches pulleys, the magnitude of this force is the same as this. So I have to use this same variable T for that cable force that I did for the other one. You with me on that? Okay, and then there's only one other type of contact force, and that's friction. And there are two types of friction. There's the friction that keeps things that are at rest from starting to move. That's called static friction. And then there's kinetic friction, which is the friction when something's already sliding. I'm just sort of arbitrarily we're only going to do problems with sliding friction. There's not really any reason, but that's what we're doing. So this is sliding or kinetic friction. That's what we're going to do problems with. One thing that you haven't seen so far is you haven't had to know anything about the direction that the things are moving, about the velocity, the direction of the velocity vector for the forces we've done so far. But to know the direction of the friction force, you do have to know the direction the thing is sliding, because the friction force is always opposite that. So for friction, you need to be told the direction of motion. You need to be given the direction of motion. You might think like, oh, well, you can look at the problem and see what the direction of motion could be. You can look at the problem and see what direction the acceleration would be, but you can't, from looking at it, know what the velocity would be. There's no way to know. It could be anything. And we'll talk about that more as we go through examples and stuff. But that has to be given. So once you know the direction of motion, the friction force is opposite the direction of motion. And another way to say the direction of motion is to say the velocity vector. So the friction is opposite the direction of the velocity vector. And the magnitude of the friction force is this Greek letter mu times n, where mu is a number that represents the two materials that are in contact. and N is the pushing contact between the two surfaces. You know, the pushing contact force between the two objects, let's say. About that mu, that's called the coefficient of friction. And it's, you know, if objects are harder to slide relative to each other, then that value is big. And if they're easy to slide relative to each other, that value is small. So like, you know, and you're always thinking of them being smooth. So like steel or something, if the two materials are steel, that coefficient is pretty small. If those two materials are concrete and rubber, that value is big. Okay. Okay, so let me do an example problem. So let's say that the coefficient of friction is 0.1. And let's say that this object is moving at this instant, its velocity vector is down this ramp. And it has a mass of 10 kilograms. So I'm going to draw a free body diagram of this. Here's the boundary. I'll start with the weight force. That's 10 times 9.81, so 98.1 newtons. And now the only contact is with the surface. And there are two things going on. There's a pushing contact and a friction contact. The pushing contact is parallel to the surface, perpendicular to the surface toward the chosen body. And I'll give it the magnitude N. And then the friction force is opposite the direction of the velocity. So it's going to be this way. That's always parallel to the surface. And it has a magnitude that's the coefficient times that pushing force between the two surfaces. And there's a Newton's third law thing with these too. It says that the friction force on body 1 by body 2 has the same magnitude and the opposite direction as the friction force on body 2 by body 1. So let me show how this works. So let's say we have an object on top of another object. Let's say this is 2 kilograms, this is 5 kilograms. And at this instant, the 2 kilogram object is sliding this way, let's say. The 5 kilogram object is sliding this way. Okay. So a free body diagram of the 2 kilogram body. There's a downward force of 2 times 9.81. There's a pushing force on the 2 by the 5. So that's perpendicular to the surface toward the chosen body. So I'll call that N. And then there's a friction force that's opposite the direction of motion, that's equal to the coefficient of friction times that force pushing the two things together. And if I gave you that coefficient, you could plug that in 0.1, 0.2, 0.3, whatever. Usually it's between 0 and 1, but it can get, like for rubber and concrete, it can get up close to 4. Okay, so now the free body diagram for the 5 kilogram. Okay, so there's a weight force of 49.05. At the bottom, there's a pushing contact from the ground. I'll call that N2, because we already named something N, and this is a different pushing force. The velocity is to the left, so that means the friction force has to be to the right. And these are two different materials, so this will be, I'll call this mu2 times N2. And now the friction force that's applied to the top of the 5 kilogram box by the 2. Well, the pushing force is perpendicular to the surface toward the chosen body. And it has to have the same magnitude as the pushing force on the 2 by the 5. So I'll call that N. And then the friction force has to be opposite the friction force on the 2 by the 5. So this way, and the magnitude is the same, so I'll call that mu times N. I know this is all a little abstract right now, but once you get into some problems, I think it'll start to make more sense. Okay, so now what I'm going to do is I'm going to do an example problem or two where it's going to be just like these, and I'm going to start with the free body diagram, but then I'm going to use the free body diagram to write out Newton's second law. remember Newton's second law says F net is equal to the mass of the chosen object times its acceleration vector. This F net is the sum of all the forces in the free body diagram. And that's the benefit of drawing the free body diagram, is you have a visual picture of all the things that you have to add up for the left side of this equation. And one thing that I want you to notice is you can often determine the line of the acceleration from the setup of the problem. And I'll do one where I show you what I mean there. So let's say that we have a cart on a horizontal surface. Let's say it has a mass of 5 kilograms. And let's say there's a force applied to the left of the cart of, let's say, 30 newtons. What's the acceleration vector of the cart? Okay, well, I'm going to start with a free body diagram. There's a weight force of 49.05 newtons. There's a pushing force from the ground, so that's perpendicular to the ground toward the chosen body. We'll call that N. And then if you go all the way around the boundary, the only other thing you have to consider at the boundary is this 30 Newton force. So that's a complete free body diagram. By the way, I'm going to, if I ever forget to mention this, anytime I don't mention it, I'm just using a standard coordinate system for my vector components. Okay. All right, so now looking at this picture, can we say anything about the direction of the acceleration? Well, this thing is only free to move left to right, okay? It can't sink into the ground. It's not going to jump up off the ground. So we can assume that the acceleration vector, I'll call it A, is horizontal. And that means I can represent it as A0, right? It'll only have an X component, no Y component. Are you with me on that? That A could be negative. I mean, it's not going to be in this case. This is a pretty simple problem where you can tell it's going to be moving in the positive X direction. But it doesn't matter. As long as you figure out like what component is going to be non-zero, the sign will work out on its own. Okay. All right, so let's put this into Newton's second law. So first, and think of each one of these as just like its own little problem from the vector problems, okay? So if you have a vector that has a magnitude of 30 and it's pointed in this direction, what are the components of that vector? You can put the tail of that vector on the origin. It has a magnitude of 30. So what would that be? Remember doing those problems? 30, positive 30, 0. Yep. You can also think of it as just the coordinates of the head of that vector. Okay, so we have that force 30, 0. Now, what about this one with a magnitude of 49.05? What would that be as a vector? Yeah, 0, negative 49.05, because it's downward. And then the last one is an upward vector with a magnitude of n. So it's like this. The magnitude is n. What would the components of that be? 0, n. It's and that's equal to the mass of 5 times the acceleration, a0. And now you have two equations. The first one says 30 plus 0 plus 0 is equal to 5a. Solve that and you get that a is equal to 6. The second one says 0 minus 49.05 plus n is equal to 5 times 0. That one tells us that n is equal to positive 49.05. This here is our acceleration vector. We just didn't know what a was, but now we do. So plug that into our acceleration vector, and you get that the acceleration is 6, 0. Units are meters per second squared. Or another way to say that is the acceleration is in the positive x direction with a magnitude of 6 meters per second squared. Any questions about that? So first you have to get your free body diagram right. Once you do that, it's just it's a vector, like a vector practice problem to come up with the components of the force vectors, and then just plug it into Newton's second law and calculate whatever variables you're looking for. Who hates this? It's confusing at first, but you'll do a bunch of them and then it'll feel like obvious, you know? Let's stop there. Yes?
So I think this is from the bottom to the output. When you the line number, it's from the top to the bottom.
Yeah, okay, so, I don't know who, I think maybe, I think people just do it either way for the most part, but some people have different habits or whatever. But remember that with vectors, the only things that matter are the magnitude and the direction. So it doesn't matter, it's the same thing, yeah. As long as this is pointing up and has the right magnitude, it's the same. Any other questions? Okay, have a good long weekend. See you next week.